Talking about buffers last time. We really kind of completed talking about buffers. We kind of completed our lecture there on buffers. So a couple important things again to talk about, when we talk about buffers. Um, as we talked about again, a buffer really is a solution that can be made really at any pH you want. The idea of a buffer is that it's able to maintain the pH even if you add some acid or base to it. Um, it will also able to do that because it's made up of a weak acid and its conjugate base, or a weak base and its conjugate acid. And again, it's really because it has both of those things in the solution to begin with that Mara, did you have a question or? Okay, just want to make sure.
No.
No, okay. I see like a hand up, so I just want to make sure. All right. So again, a buffer really because it has both of those components in it, the weak acid and the conjugate base, or the weak base and the conjugate acid. It's able to really prevent the formation of free H plus or free OH minus, when we add additional acid or base to it. And that's ultimately really, how a buffer functions, because it has both of those things present. When you add more acid or base, again, it essentially sort of ties up, if you will, the H plus that's being added or the OH minus that's being added and stuff like that. So, that's essentially, how it functions. So we talked about sort of calculations with it, and really that's where you should be using the Henderson-Hasselbalch equation. Really, buffers are common ion type problems, so you want to use that Henderson-Hasselbalch equation to really calculate the pH. You also, as we talked about and sort of showed as well, you can use an ice table to do that. It's really kind of your preference, but the Henderson-Hasselbalch will be kind of a sort of maybe quicker approach to calculate those things. In addition, when we do add acid or base to a buffer solution, remember that we are constantly, again, changing the volume, which is going to affect the molarity. So we do want to first do that ice table in moles. So always when we add solution, first ice table in moles, and then afterwards, you do want to convert back to the molarity of the solution, and then continue on with the calculation that you need. So we're going to see that coming up here in titrations, which is what we're going to talk about here now. That sort of same concept of, obviously in the titration, we're continuously adding volume. So we do want to do that first ice table in moles, and then afterwards, we want to convert it back to molarity. So it's just really good practice to kind of do it that way. All right, any questions on buffers or that stuff that we talked about last time? Okay, so we're going to now pick up after buffers here and talk about titrations. Titrations really is kind of the next big topic that, we really do cover in this class. It's another topic where you really do have to sort of conceptually understand what is going on in the problem in order to sort of, really do the calculation. The good news is there's going to be some different calculations that you'll have to do depending on sort of where you are in the titration curve. The good news is you've already done all these calculations. The hard part for a lot of people is to figure out when to do these sort of calculations that you sort of already know how to do. So that's, again, where the conceptual part of titrations come into play, understanding where you are in terms of on the titration and what's happening. So just to sort of review, I'm sure you probably have done a titration before, perhaps in your career here, or seen a titration, but a titration is really a process that we use where we add, we added some volume of a solution to another solution. Usually one of those solutions is sort of a known solution. What I mean by that, we know the concentration, we obviously know how much we're adding. The other one has some type of unknown aspect to it. Usually, maybe we don't know the concentration of it, maybe we don't know the molar mass of it, or something like that. So we could do this process basically and we will make a chemical reaction that occurs. And when the solution is basically complete, we could do some calculations to do that. A titration is usually basically done by using a burette, which is what's pictured there on the bottom. That's a burette right there. Basically, just a long sort of cylinder, right, that you add to like a flask. And right here, again, is what's referred to as a stopcock. That's basically what opens it and shuts it. And you basically can add the solution slowly to another. In an acid-base titration, like we're going to mainly talk about here, sometimes it's the base up in the burette and the acid in the bottom. And sometimes it's the opposite. You could have the base or the acid up here and the base down on the bottom. So it does depend on the type of titration you're going to be doing, but the idea is to really kind of slowly add from the burette into another solution, causing a chemical reaction to occur. How far do you go? Well, you continue to do this until the reaction is complete or until you reach what is usually referred to as the equivalence point. So the equivalence point in titration, especially in an acid-base titration, is the point where the moles of the acid will equal the moles of the base. So in an acid-base titration, that's basically what's sort of meant by the equivalence point. We've hit the point where exactly those two guys are pretty much equal to each other. How do we know when to stop? Well, usually we do use an indicator, which we'll talk about as well. Indicator is basically a substance that will change color. And it usually works by a pH range, actually. So an indicator actually uses, kind of works over a specific pH range, and it changes color. So, you're probably familiar with phenol phalene, and that's the common sort of indicator it's used in a lot of acid-base titrations. It is colorless in acidic conditions. It's actually colorless in neutral pHs. It actually turns pink in basic situations. And so that's probably, again, the indicator that you maybe have used before. That's actually probably the indicator that we're seeing down here at the bottom. Again, no color to begin with, so that probably implies that this is like an acid. This then turns this very, very light shade of pink, and that indicates to you that you should stop the titration at that point. You've reached the equivalence point. Another sort of terminology that we sometimes hear when we do a titration is what is referred to as the endpoint of a titration. The endpoint of a titration is kind of where you pretty much stop. In a good titration, your endpoint should be pretty close to your equivalence point. Hopefully, they should be very near each other. Now, for example, phenolphthalein, by the way, works, somewhere in a pH range of like 8.3 to 10. So if you ever done a titration with phenolphthalein or talked about a titration that uses phenolphthalein, usually what they tell you is you want to stop like at that very, very first sign of pink, like so faint pink that you got to put like a white piece of paper underneath it to kind of see the pink color. And that's because at about 8.3, for example, in terms of the pH, it's really colorless. And as you kind of head down towards 10 in terms of the pH, it gets really, really pink and dark, dark, dark pink. So the idea when they tell you, get just a lightest shade of pink, it will kind of put you in probably this range, this part of the pH range. And probably for the titration that you were doing, that's probably the appropriate area where the equivalence point would be. Now, we always want to kind of choose, and we'll talk about this a little bit later on here, but we do want to choose an indicator that actually does change color as we are near the equivalence point. So that's obviously the purpose of choosing the proper indicator when you're doing a titration, is to make sure that you can sort of visually see the color change occur, as you're nearing that equivalence point. Any questions on that there? So You may also wonder, or if you ever done a titration before, or even done titration with phenolphthalein, there's a really common thing that people oftentimes will say when they do a titration, and that is that, I just added like one more drop and it turned like dark pink. Like it wasn't pink at all to begin with. It was really colorless. I just added one more drop, one single drop, and it just kind of shot from like no color to really, really dark pink. And that's a common occurrence when people do titrations. And we'll actually talk about, why that happens here as we go through these different titrations. But there's actually a reason why, that sort of happens when you just add one drop and it kind of goes from like no color to really, really super pink. And it really does is based on the idea of how indicators work, which is they work over a specific sort of pH range. All right, so let's talk about the first type of titration. First type of titration is going to be a titration of a strong acid and a strong base. So we'll just say something like hydrochloric acid, which is a strong acid, plus some sodium hydroxide as our base. We will get a reaction of some water and some sodium chloride. So just to make sure that everybody's on the same page in terms of sort of the setup that we're working out here, up in the burette here, in this titration, is the sodium hydroxide. Down in the beaker or the flask or whatever you may be having your guy in there is our HCl. So we're adding our sodium hydroxide to our HCl. We obviously have an indicator there as well. And let's talk about this curve here. This is a titration curve. This isn't the entire curve. On the Y, we have the pH. In this case, since we are adding sodium hydroxide, we have the volume of sodium hydroxide added. And this sort of S curve that we see here in the titration graph is a very common shape that occurs in a titration here. So what we're going to talk about is how we calculate the pH anywhere along this sort of titration. So you decided to titrate and you decided, you know what, I'm not going to stop at the equivalence point. I'm going to take it all the way past the equivalence point, which is how we get to the kind of the top of the graph that's over here. So there's usually in a titration curve kind of 4 different parts. And, the first part is, kind of before you start the titration. What I mean by that is, you haven't added any base in this case. So the only thing you have sitting there is in the beaker potassium hydroxide, say that right, hydrochloric acid. So the only thing you have in there in the beaker is some hydrochloric acid. So we want to know, what would the pH be, before we even start the titration? And we can figure that out by thinking about what we have in the beaker. So really at number 1 here, before we start the titration, as I mentioned, we essentially only have the hydrochloric acid. And what is hydrochloric acid? Well, to figure out the pH, because hydrochloric acid is a strong acid, we know that it is going to 100% break apart into H plus and Cl minus. This means that because it's a strong acid, pretty much the concentration of the hydrochloric acid we're starting with would be the H plus concentration, which means we really can almost directly go right into our pH equation to figure out, what the pH of our solution is before we begin. We could do it in molarity because we have not added anything, right? So there's no addition. So whatever the concentration of that strong acid was to start with would most likely be your H plus concentration. And because that's the H plus concentration, we could go right into our pH equation and get the pH. It's acidic, it's a strong acid, so it is starting, if you look at the graph, in the right location. It is starting acidic, right, as we would expect at this point. So before we start the titration, in a titration of a strong acid and strong base, we essentially have only the strong acid present, which means that we can just go right into the pH equation to get the pH. Any questions on that? Okay, then let's talk about what happens when we actually start the titration. So that point where we, add that first drop all the way up here to the equivalence point. Call this number 2. What is happening in this area of the titration curve? Well, we're clearly adding sodium hydroxide at this point, which means we are going to get a chemical reaction to occur, and that is this guy. We are before the equivalence point. As we can see here on the graph, we're definitely before the equivalence point. So let's talk about what happens before the equivalence point. So this is before the equivalence point. It is after, obviously, we started adding some sodium hydroxide in this case. We will get a reaction between the hydrochloric acid and the sodium hydroxide. And it will do that same reaction that we just talked about. Now, let's talk about a couple of things at this point. First off, let's talk about, we're going to do an ice table. We need to do an ice table to figure out what is happening as a result of adding that sodium hydroxide to the hydrochloric acid in this titration. When I do this ice table should definitely be done in moles because we are adding volume, which means the molarity is changing, right? So just like we talked about with buffers, and it happens pretty much all the way through titrations, because you're just constantly adding volume from the burette, you need to do these ice table in moles. Now, when we look at these two things, we could kind of think of the HCl and the sodium hydroxide by what is happening with it. This is really what we're starting with in like the beaker or the flask. This is what we're adding. And I'm just going to make up a number. So I'm going to make up a number for hydrochloric acid of, I'm going to start with 4 moles. Okay. So because I'm before the equivalence point, should the moles of the sodium hydroxide be less than, more than, or equal to the moles of the HCl? To help you sort of make that decision, let's talk about the equivalence point here, right? What happens at the equivalence point? As we talked about the definition of the equivalence point, that's the point where the moles of the acid will equal the moles of the base. So in this case, we have not hit that point yet because we're before the equivalence point. And what that tells us is we're before the equivalence point. So the moles of what we're adding should actually be less than what we started with. So again, I'm just going to make up a number, which is 2 moles in this case. So again, the moles of the sodium hydroxide here, which is what we're adding, because we're before the equivalence point, should be less than the moles that we started with. And again, that's because we're before the equivalence point. You could think of the equivalence point as that definition of they're equal. So obviously before they could be equal, we kind of have to build up to get the equal in terms of our sodium hydroxide. Any questions on that there? Now we will assume 0 moles over here. So kind of like what we did with the buffer in this case, when we do a change that's going to occur here, we're actually going to use a number. And we could think about it pretty simply in terms of, at this point, there's definitely less moles of base than acid, which means we're going to use up all of the base as it's like the limiting reagent in this case. So the change that would occur here would be the smaller number, which is minus 2 moles in this example. Minus 2 moles plus 2 moles. That means when we reach equilibrium, we have 2 moles of this guy, none of that guy, again, like the limiting reagent, and 2 moles of this guy. First off, any questions on the table here? Just like in buffers, after we do this first ice table in moles, it is very good practice to convert these guys back to molarity. So we would convert this to molarity. We would convert this to molarity. Obviously, the volume here would be the total volume at this point. And what would that be? That would be the volume of HCl we started with plus the volume of sodium hydroxide added, converted to liters. All right, so at this point, what we want to do is we want to figure out, what the pH is. So we again could use our ice table to help us do that. And when we use our ice table to help us do that, we could kind of see what is here or what is present at this point in the titration. So if we look at the ice table, we can see that we have HCl and sodium hydroxide left over at this point. And you may say to yourself, well, if I want the pH, that clearly is like the Henderson-Hasselbalch buffer situation. And again, no, it is not a buffer. These two guys are not a buffer because this is hydrochloric acid, which is a strong acid, which means it cannot be a buffer. That is sodium chloride, which we already know is a salt, and that salt is neutral, which means not important here, right? Because this is a neutral salt. Which means really what we're left with at this point is a strong acid. And so we're really left with a strong acid, which is HCl. And now we can use the new molarity here to go into our pH equation and get the pH at this point. So in this type of titration, once you start the titration, it does require one ice table to be done in moles. The purpose of that ice table is to figure out what the new concentration of the strong acid is, and then you can go into obviously the pH equation at that point. So anywhere in this range, from that moment you add that first drop until that moment when you hit the equivalence point or before the equivalence point, again requires that one ice table done in moles. The result of that is you will still have your strong acid left over, and then you could go into your pH equation to figure it out. Any questions on that there? Okay, so let's talk about what happens as we approach the equivalence point. Well, we see on this titration, we're starting to get a little bit more basic in that sense, right? The pH is starting to go up, I guess is a better way of saying that. And that makes sense since we're adding sodium hydroxide, which is a base to it. So we start to see an increase in the pH. What we typically see is as we get towards the equivalence point, we can see, as we see here, this kind of jump in pH that occurs to this equivalence point. By the way, we also see a jump after the equivalence point that occurs. But more importantly, when we look at the equivalence point and heading to the equivalence point, what is happening in terms of the pH? Well, the pH is making a very big jump. The pH is pretty much going straight up. But because the pH is going straight up, it's pretty vertical. And what does that mean about the volume we're adding? It means that the volume we're adding as we approach the equivalence point is not a lot of change. So, what does that mean in terms of that little question that you oftentimes hear people say when they do titrations? I only added one drop and my color, my indicator went like to super dark pink. Again, a reminder that if you look at something like our phenolphthalein, again, closer to the 10 versus the 8.3, it gets like super, super, I know it's red, we'll pretend it's pink, super, super dark, pretty much pink at that point, almost colorless at this point, and then like a tinge of pink starts to occur as you kind of get closer down towards 10. And the reason why when you only add one little drop, like that drop in there, and then it turns this thing like super dark pink, is because as you get close to the equivalence point, as you can see on this graph, it goes pretty vertical, which means you do not have to add a lot of volume to change the pH a lot. And one drop could maybe take you from a pH of here all the way up to like a pH of here, perhaps, or even here and stuff like that, or even here. And even that one drop could even take you up to a pH of here, which would be about pH of 10, 11 in that park, which would turn your solution really, really pink. So because as we approach the equivalence point, it goes fairly vertical. That means you don't have to add a lot of volume, a base in this case, for example, to change the pH by a lot. And that's why we can sometimes see, again, that color of the solution change super pink very quickly, because even though you only added one drop, you did change the pH a lot, and the indicator is going to show that in the color that you see. Any questions on that? And if you've ever done a titration, people usually yell at you, make sure you get that light, super, you can barely see the pink color type of thing. And you should try to do that. If you missed it by a drop, would it make a very big difference in your calculation? Let's say you just added one drop and you ended up here, versus you ended up here at the equivalence point. If you just go straight down, is there a very big difference in terms of that pH or the volume? There's not, which means in reality, even if you missed it by like a drop or two and it went really dark pink, it probably would not have made a tremendous difference in your calculation, because again, if you just go vertically down, it's about the same volume almost as what you have at the equivalence point to even up here. And the truth is, it probably wouldn't make that big of a difference, even though people yell at you all the time. The really reason why they yell at you all the time is people are not really careful when they do titration. So a lot of students and stuff don't really add like drop by drop. They open the thing up and just let it drop in, right? And if you're not really careful and going drop by drop, you could achieve that same dark pink color and actually be over here, right? If you just let it drip in there all the way through and you missed it by more than a drop, it could put you over here in that very dark pink color. And in that case, it would make a tremendous difference, obviously, in your calculation. But, if you're being very careful, kind of going drop by drop, really slowing yourself down as you approach the equivalence point in your titration, and you accidentally add one drop or two drops too many, in the grand scheme of things, in terms of calculation, not going to make a tremendous difference. But if you're really not being careful and you just kind of like open it up, like I used to do titrations, open it up, shut it, it turned pink, I'm done. You might find yourself over here, and you're actually pretty far away. And you wouldn't have any kind of difference in the color per se. It might be a little bit darker, maybe if you were way, way over there. If you're kind of careful and going slow, you actually, even if you missed it by a drop or two, probably would be okay in terms of your actual calculation. Any questions on that? All right, then let us then actually talk about what is happening here. We'll call this part number 3 here. Right there at the equivalence point. So right when we hit the equivalence point, let us talk about what is actually occurring. And we'll do that here. All right, so let's say we hit the equivalence point now. Well, clearly at the equivalence point, we're going to still have a reaction between hydrochloric acid and sodium hydroxide. We're going to still be making some water and some sodium chloride. Again, here, just for a reference point, this is what we're starting with. This is what we're adding to it. We will do an ice table. It again should be done in moles because we're adding volume, obviously. I will start with my same made up number of 4 moles for my hydrochloric acid. What should I have for my moles of sodium hydroxide at this point? Well, because I'm at the equivalence point, the definition pretty much is the moles of acid should equal the moles of base, which means I should have 4 moles of sodium hydroxide at this point because I'm at the equivalence point. Again, we will have 0 here. The good news is you can't really pick the wrong number since they're both 4. So we're going to -4 in this case. -4 and +4 can give us 0 this guy, 0 this guy. We'll end up with 4 moles of this guy. Again, using the total volume to reach the equivalence point in this case, we could convert that back to molarity. Any questions on that ice table? What do we have left? So again, our ice table could help us. We have our good friend sodium chloride left as a salt. That sodium chloride, when it breaks apart into a sodium ion and a chloride ion. And as we talked about before, sodium is group 1, which means it's neutral in terms of salts. Chloride came from hydrochloric acid, which is strong, which also means it's neutral, which means the pH at this point in the titration should be a pH of 7 at the equivalence point, because the resulting solution, once you reach the equivalence point, is only a salt that will not go through hydrolysis, and that is considered a neutral salt in that case. Any questions on that? So the good news is not much of a calculation at the equivalence point here. It would be a pH of 7. Now, in normal titrations, that is probably where you lay it up and you stop. But sometimes if we want this titration curve, we continue on. And that brings us to sort of the 4th part of this titration curve. And the 4th part of the titration curve is after the equivalence point until basically you stop. Yeah. So let's talk about what happens if we decide, well, that's nice, it turned color, my indicator. I'm just going to keep going. Why not? I got some extra base. You might have done this without knowing you did this in a normal titration if you've ever done one. And it's very common at the end of the titration, you're like done with your titrations. People just open up their burette, let all the sodium hydroxide basically drain into their beaker, and you're basically continuing on with your titration at that point. So let's talk about sort of what is happening there. And actually, let me go back here so I got somewhere to write. That will work, I think. That should get, all right. So let's go after the equivalence point. Now, after the equivalence point here, we are still going to have our reaction of hydrochloric acid plus some sodium hydroxide going to our water and our sodium chloride. Again, as we've been talking about, this is what we're starting with. This is what we're adding. But now we are past the equivalence point. So if you think about our moles of acid to moles of base at this point, at the equivalence point, they're equal. Once we go past the equivalence point, we're pretty much just dumping base in there. So we have more base than acid. So again, using my made up number, starting with my 4 moles of HCl, because I am past the equivalence point, I should have more moles of the base in this case. So I'll use 6 as a made up number. What happens at the change part here? Well, we kind of have a switch that occurs. This HCl that we started with now becomes like the limiting reagent. We have plenty of sodium hydroxide in this case. This becomes like the excess reagent. So the change always has to be the smaller number. Otherwise, you get a negative number, which is not good. So this is going to be -4, -4, and +4. Means 0 there, 2 moles there, and 4 moles there. Just like we've done on the other ones, we want to convert back to molarity using the total volume that we've added plus the volume that we started with of the HCl. So again, if you're not sure what's going on here, we can look at our ice table and see what things we got left. We got sodium hydroxide left. We got sodium chloride left. So as we've talked about up to this point a number of times, sodium chloride is a neutral salt, so we're not going to worry about it in terms of the pH, which means we should not worry about that. Also means we should not be using a buffer here either, because they are not even related to each other. So again, just because you have two numbers, don't use the buffer equation. What we essentially have here is a strong base that's left over. And because that's a strong base, that will give us our OH minus concentration. And once we have the OH minus concentration, we could get first the POH. We then can subtract 14 and get us to the pH at that point. So in this type of titration, after the equivalence point, requires, again, an ice table to be done in moles. The result of that ice table will actually tell you how much strong base you have left over. You then can use that strong base to figure out the POH and then the pH. Any questions on that there? Okay, so that takes us through this first type of titration all the way through. A couple of things here about it. You should be able to figure out the pH anywhere along this curve. There's a couple of things that people sometimes have trouble with. First off, how do I find like the volume of the equivalence point? Well, if it is a 1-to-1 relationship between the acid and base, you can use M1V1 equals M2V2 to do that, to figure out the volume at the equivalence point. Sometimes they don't tell you. You could also do, which is really what M1V1 equals M2V2 is doing, which is a stoichiometry problem where perhaps you have the volume of the acid. I'm sorry, you have like you have the volume of the acid, or you could do like let me spit that out right. Take the volume times, actually, I'll put it this way, hang on. Yeah. I'm going to erase that, try it again here. Come here, there we go. All right. So in a titration where they maybe tell you, hey, you're starting with 25 milliliters of this acid at a certain molarity, what's the equivalence point when you add like the molarity of a base to it. So you basically can do a liters times molarity calculation with the acid and get the moles of the acid, and using the moles of the acid and the stoichiometry from the equation, like 1 mole of acid equals 1 mole of the base, will give you the moles of the base. And since you have the molarity of the base, you can use the molarity of the base to figure out the volume of the base that you would need. So that's really what this calculation is doing. It's basically a stoichiometry calculation, depending on sort of what you're given. You could be given these two pieces of information. You could be given the molarity and the volume of the base and, just the molarity of the acid. But, so there's a couple different ways you could do it, but basically a stoichiometry problem. But you could use M1V1 equals M2V2 as long as it's a 1-to-1 relationship between the acid and base. If it's not a one-to-one relationship between the acid and base, then you cannot use that. You do have to do the stoichiometry sort of calculation, because if you use the M1 V1 equals M2 V2 and it's not one-to-one, this part of the calculation really will be incorrect, the multiple relationship part. So you need to make sure that you do a real stoichiometry calculation. But most cases that you'll come across, probably you can use that M1 V1 equals M2 V2 calculation, and you'll get the right answer. So why don't we try just an example of one here? Let's go with, let's do this here. Oops, come here. Let's say we did a titration starting with 25 milliliters of 0.1 molar hydrochloric acid. What is the pH after, we'll go with 18 milliliters of 0.1 molar sodium hydroxide is added? All right, take a minute or two to see what you come up with in this case. Again, the titration here is basically what we've been talking about. Sodium hydroxide up in the burette, hydrochloric acid in the beaker. So we're adding the sodium hydroxide to the HCl. Okay, let's take a look. So clear we're doing a titration. So we're going to need a reaction there. And write that out there. So again, it's the same one we've been looking at. So obviously our sodium hydroxide and our hydrochloric acid are going to react. Going to get some water there, and we're going to get some sodium chloride. We obviously are doing a titration, so we do need to get the moles of each of these. So to get the moles of our HCl, it's going to be 0.025 times our 0.1. Right, that's going to give us 0.0025 moles. And again, that is 0.025 liters, which is our 25 milliliters, times it by our molarity of our acid, giving us our 0.0025 moles of HCl. We'll do the same calculation with this guy. That's going to be 0.018 times 0.1, gets us 0.0018 moles of this, and none of that. Again, that done the same way, our 0.018 liters times our molarity of 0.1 moles per liter, giving us 0.0018 moles of sodium hydroxide. Any questions at that point there? Now, a very important thing when you're doing titration problems is to understand sort of where you are in the titration. And you actually can use your ice table to help you determine sort of where you're at. And again, remembering that in this case, this is what we started with. This is what we're adding. And if we do a quick comparison of the moles of sodium hydroxide to the moles of HCl that we started with, we could see that the moles of sodium hydroxide in this case is less than the moles of HCl. So what does that mean? That means that at this point, we are before the equivalence point. So that is how we could kind of use those numbers to determine that we're before the equivalence point. Remember, if we were at the equivalence point, the moles would both equal the amount of HCl that we started with. So again, we have an idea as to where we're at in the titration. We're before the equivalence point. Because we're before the equivalence point, that means that the moles of sodium hydroxide will be our limiting reagent and the actual change that we should be doing here. That means when we reach equilibrium, we will end up with 0.0025 minus 0.0018, giving us 0.0007 moles. Nothing here. 0.0018 moles at this point. Any questions on the ice table here so far? Now, as I mentioned a number of times at this point, once you do this initial ice table in moles, you should convert back to molarity. How do we convert back to molarity? Well, we want the total volume, and that would be these two guys. Remember that we started with 25 milliliters in the beaker. We added to it another 18 milliliters of sodium hydroxide. That's going to get us 25 plus 18, a grand total of 43 milliliters at this point of total volume. We're going to convert that to liters and divide by that number here, which would be 0.043 liters. And if we do that, 0.0007 divided by 0.043 gets us a concentration here of 0.0163, we'll call it. This guy here gives us a concentration of 0.0419 molar, right? This is molar. At this point, if you're still not sure what is happening here, even from knowing you're before the equivalence point, the ice table again can help you determine what you got going on. We have hydrochloric acid here, which is a strong acid left. We have sodium chloride over here, which at this point we've talked about a number of times, still a neutral salt. So even though we got two numbers here, you shouldn't be using this number really at all at this point, because that's a neutral salt, not going to have an effect on the pH. Any questions on that there? That means that really what we have at this point is HCl that has a concentration of 0.0163 molar. And because that's HCl, that is also the H plus concentration. That means we could go into our pH, which is minus the log of 0.0163. What did I get there? 0.163. There we go. And that gives us a pH of 1.79 at this point. Any questions on that calculation? Okay. So we could kind of see where we're at in terms of the curve here. We're definitely, before the equivalent. Oops, come back. We're before the equivalence point here. And we added about 18, which is in here. We got 1.7 something. Whatever we got there, 1.79, and that fits between those two numbers. So we probably did pretty well in this particular example. Any questions on a titration of a strong acid and a strong base? Okay. The next type of titration we're going to talk about is a little bit different, kind of similar, but still a little bit different. And this is going to be a titration of a weak acid and a strong base. So this is going to be a titration of a weak acid and strong base. So we could look at something which is a similar one to a lot of titrations you've done, which is sodium hydroxide and acetic acid. So the relationship in terms of what's happening is kind of similar to last one. We're going to have our sodium hydroxide up in the burette, our acetic acid here down in the beaker. We're adding our sodium hydroxide to our acetic acid. So what are these things? Well, obviously sodium hydroxide is a strong base. And this is obviously a weak acid. So again, adding a strong base to a weak acid, we see a similar type of S curve that's happening. We also see we're starting a little bit higher. Again, we're starting with like a weak acid, right? So we're a little bit higher up there in pH than we were with that strong acid, which started down here. We also see that vertical approach to the equivalence point. So we still see that verticalness that occurs. We also see that jump to the equivalence point and also a jump in pH after the equivalence point. and kind of the leveling off of the pH at some point. So much like the previous one, there really are 4 different points along the way here. And let's talk about maybe some of the differences and how you handle these calculations. Let's start again. We'll call this kind of number 1, which is at the start of the titration. So before you add any sodium hydroxide, start of the titration, no base added. So what do we have going on in this case? So before we add any base, the only thing we have is our weak acid. So how would we find the pH of a weak acid? Well, it's a weak acid. It is really a Ka problem, which means we take our weak acid, we break it apart, because we have not added any sodium hydroxide at this point. We could do this table in molarity, 0 and 0. Change would be minus x plus x plus x. At equilibrium, molarity minus x, x and x at this point. We can solve for x using our Ka, like we've done before in a previous chapter. That x will equal the H plus concentration, and then you could obviously go into the pH at that point. So already you can see in this type of titration, it is a little bit different than our strong acid and strong base. And that's because, again, here we're starting with a weak acid. So we do have a little bit more work here to do to figure out our kind of initial pH, but it is really based off of the weak acid, its concentration, and a Ka type problem. Any questions on what happens at the beginning of the titration there? Okay. So then let's talk about what happens when we start the titration. So when we start the titration, just like in the previous one, from that very first drop, if you will, all the way up to our equivalence point there, we'll call this number 2. So clearly we are adding some sodium hydroxide here. So we're going to get this reaction to occur. Let's see if I got somewhere right. I do, I hope. All right, we'll go there. So number 2 is really going to be before the equivalence point. And again, we will get a reaction. So it's going to be our acetic acid plus our sodium hydroxide. Going to make some sodium acetate. Oops. And some water here. Got a little extra negative there that I don't need. Come here. Okay, so it's important to remember, again, when you're doing this sort of, this is again what we're started with. This is again what we're adding. So remember that before we're at the equivalence point sort of our thought process of they're got to be equal. So before we get to that equal point, whatever we're adding needs to be less than what we started with. So again, I'm just going to make up numbers and call this 4 moles of acetic acid. I again need to do this ice table in moles because we're adding volume. Because we're before the equivalence point, again, I'm just going to make this less than those starting moles, and we would have 0 at this point. Because we are before the equivalence point, our sodium hydroxide is really the limiting reagent here. It gets used up, and it will be the change that's occurring. That means when we reach equilibrium, 2 moles of acetic acid, 0, and 2 moles of our sodium acetate. Any questions on what that ice table looks like? Okay, so just like we've been talking about, you should at this point, using the total volume, convert these guys back into molarity. But how do we get to the pH? So that's the question. Well, again, your ice table can help you with that. At this point, we have acetic acid left over. We got sodium acetate left over. Hopefully you can recognize that these two things are related to each other, right? Those two things are a weak acid and its conjugate base. That is also known as a buffer at this point, right? And because it's a buffer at this point, we could actually go right into the Henderson-Hasselbalch equation to figure out the pH. Or if you don't want a Henderson-Hasselbalch, you could do an ice table where the equilibrium concentrations are your initial. So the equilibrium from first table are your initial in the second. Again, as we've talked about, probably less room for error, but you could definitely do an ice table. Again, the ice table would be based off of acetic acid, breaking apart in this case. And the key of that one would be you should have a molarity here, and you should have an initial molarity here. The rest of it would be X's, and obviously solve for X, and that will give you your H plus concentration. Any questions on what happens before the equivalence point in this type of titration? Again, as you can see, a little bit different than what was happening with our strong acid and strong base. Any questions on that? So that occurs, really all the way from when you hit that first point to before the equivalence point. You really create a buffer in this region. So you're really creating like a buffer in that particular region. And again, that's why it's sort of maintaining a little bit of the pH as you kind of go through here. Let's then talk about what happens in this type of titration once we reach that equivalence point. We'll call it number 3 here. So number 3, which would be at the equivalence point, so again, we're obviously adding, so that is going to require our reaction. Again, this is what we're starting with. This is what we're adding. And because we are at the equivalence point, those two guys should equal each other, right? So that's what that means. Moles of the acid equals the moles of the base. So using my made up number of 4 moles would mean that I should also at this point have 4 moles of sodium hydroxide and none of that guy. Change at this point would be -4 plus 4 moles, which means at equilibrium, like I would expect, all my acid is gone. All the base that I added is gone. And we do have 4 moles of this guy, which again can be converted back to molarity by using our total volume at this point. Any questions on that part of the table there? Again, here, looking at what we have left at this point in the titration is this guy here, which is a salt. So this salt, though, is a little bit different than sodium chloride that we encountered earlier. This salt will break apart into a sodium ion and an acetate ion. Again, the sodium ion coming really from sodium hydroxide, not going to go through hydrolysis. But what about our acetate? Well, our acetate comes from this acid, which is a weak acid, which would imply that this guy would go through hydrolysis. So in this type of titration, at the equivalence point, you need to do an ice table here, followed by another ice table. The second ice table here will be that salt that will continue to react with water. And because it comes from a weak acid, it's going to act as a base, which means it's going to accept the H+. When it does, it will produce acetic acid where it came from, and it will produce hydroxide. Now, at this point, we know several things. It is producing hydroxide, which means we know that this solution at this point should be basic at the equivalence point. Again, different than our strong acid and strong base, which was neutral at the equivalence point. This guy is going to be basic. Also means that we should be using a KB value in our calculation, which probably means we don't have that value. So again, you'll probably need to do the Ka times Kb equals Kw move here. But we will need to do an ice table here. And where do we get the initial concentration? Well, the initial concentration is going to come from the previous table. So this guy right here would be what we would use right there. So I'll turn them red. So we would use the concentration from the previous table as our initial concentration here. This would be 0, 0, and the rest of the table will be X's. You know, typically if you're using molarity, X's is kind of what you use. Molarity minus X, X, and X. At this point, as I mentioned, KB is what you need to put that into. You would use the KB value and expression and solve for X. Important to remember when you do solve for X, X is not the H plus concentration, but it's actually the OH minus concentration in this case. That's going to allow you to get to the POH and then eventually to the pH. So you could clearly see at the equivalence point in this type of titration, there is a lot more going on than writing a pH of 7. So to recap, when you get to the equivalence point in a weak acid, strong base titration, it requires really 2 ice tables. The first ice table is to really figure out what is the concentration, the molarity of your salt, followed by a second ice table, which is really a hydrolysis problem of your salt going through hydrolysis. This is also why it's really important after you do the first ice table to convert this thing back to molarity, because you probably will get the wrong answer if you try moles in here on the bottom. It does need to be concentration. So again, first ice table and titrations, moles, but really, really good practice and will not screw you up in later calculations if you convert back to molarity immediately after that first ice table. So you should just keep that in mind. Otherwise, again, you'll probably end up with the wrong answer as you come down into this ice table down here. Question on what is going on at the equivalence point here. So that takes us to our equivalence point. And again, we can see here at the equivalence point in this particular titration, it is a pH of 8.72, which is definitely basic and like we would expect, because we're really generating a salt. We're generating a basic salt, and we would expect it to, again, to be in that basic range. Any questions up to there? Okay. Then let's talk about what happens here as we go past the equivalence point here. So we decide, hey, that indicator changed color. That's okay. We'll just continue on and see what happens here in sort of the fourth part of the titration curve. And just give me one. So we're going to be looking now in this titration as we go past the equivalence point here. So kind of number 4 here, past the equivalence point. Again, obviously, like the other parts along the titration curve, we're still having our reaction occurring. And it obviously is the same reaction that we saw all the way through here, and a little bit of water. All right. So just like everything else, we want to do this first ice table in moles. We're past the equivalence point. So again, in this case, we have a change that's occurring. We know that our moles of sodium hydroxide, which is what we're adding, should be greater than the moles of the acid we started with in this case. And again, since we started with this and we added this, we should know, since we're past that equivalence point, again, using my made up number 4, that again would mean then perhaps I have 6 moles of sodium hydroxide at this point. Again, that change occurs here past the equivalence point. My acid now becomes my limiting reagent. My base becomes my excess reagent. And that's really going to affect the change part. Again, you can't have negative numbers, so always small numbers what you want to go with. So we're going to do this. That means nothing there, 2 moles there, and 4 moles here. Again, as we've been talking about a number of times today, we want to make sure we do kind of convert these guys back to molarity. And we could see what we have left over at this point is sodium hydroxide and sodium acetate. So you may be thinking to yourself, well, I got 2 numbers. Henderson-Hasselbalch seems like a good move. But hopefully you can see that these 2 things are not related to each other. So sodium hydroxide and sodium acetate, not related to each other, not a buffer, so you wouldn't want to use it here. So let's talk about the 2 things that we have. Well, we definitely have sodium acetate like we saw at the equivalence point that will go through hydrolysis, right? And it will produce OH minus through that hydrolysis reaction, basically acting as a base, right? But we also have at this point sodium hydroxide, which is a strong base. Now, between the 2, sodium acetate is a much, much, much weaker base. You could kind of think about it this way. In order for the sodium acetate to go produce hydroxide, it's got to go find water, it's got to do a reaction. And for the sodium hydroxide to produce hydroxide, it pretty much just needs to go for a swim. It's going to break apart. What that means is between the 2, the major contributor to the pH here at this point would be the strong base. Although the sodium acetate is contributing, it's probably not contributing as much as the sodium hydroxide would. And that means at this point in this type of titration, we ignore the salt's contribution. Again, because out of the 2, sodium hydroxide is a much, much stronger base. Again, it just needs to go in and it's going to break apart. And by that process, it's going to produce hydroxide very, very quickly. So it's really going to be the one that's going to be majorly contributing to the pH. What that means is because that is a strong base, that pretty much will be our hydroxide concentration. And because that's our hydroxide concentration, we could get the POH. And from that, we can get the pH. Any questions on that there? So you can see in this type of titration, although the curve may look very similar, although it may kind of appear to be a very similar sort of calculation, our titration as the strong acid and strong base. There's really 4 distinct parts. The first part is really a Ka problem. Part 2 is really a buffer. Part 3 is a hydrolysis problem. Part 4 is a POH type problem. These are all problems that you know how to do. The key and where people run into a lot of problems is they have no idea where they're at in the titration curve. Actually knowing where you're at in the titration curve can make the calculation part tremendously easier, because even before you do the calculation, you should go like, oh, I'm like before the equivalence point, I should be doing some type of buffer. I'm past the equivalence point, I should be doing something with a strong base. I'm at the equivalence point, I should be doing like a hydrolysis problem. So understanding where you are in the titration and knowing that can help you before you even do the calculation, what type of calculation you should be doing, which is really important in these type of problems. People sometimes just jump in and try to figure it out as they're going along, and a lot of times people get very lost in terms of that. Any questions on that there? So why don't we try one here to finish up on, let's find that page. Oops. All right, let's say we did a titration of 25 milliliters of 0.1 molar acetic acid with, let's go with, let's go with 21 milliliters of 0.1 molar sodium hydroxide. The Ka value for acetic acid, 1.8 times 10 to the minus 5. So what is the pH at this point in the titration? Same idea here. We're adding the sodium hydroxide to the acetic acid. So take a couple of minutes to see what you come up with. Obviously, we're doing a titration. So, you know, there's a lot of information in the problems as we've kind of been talking about as we go through these chapters. And it's important to sort of understand, you know, what's going on and what's happening. First off, I got acetic acid and sodium hydroxide. I got a Ka value for acetic acid. So that automatically tells me, if I was not sure, that I'm dealing with a weak acid. We hopefully should know that sodium hydroxide is a strong base. So again, I could know just from the outset of looking at this problem that I'm dealing with a weak acid and strong base sort of situation. I also can then think about the weak acid, strong base titration curve that we just talked about, and I might want to figure out, you know, where I'm at. So before I could do that, perhaps I need to figure out the reaction, which is obviously the same one in this case that we've been looking at. And because I'm definitely doing a titration here, I definitely want to make sure that I do this table in moles, right? So that means that I do need to calculate the moles of each of our guys. So we're going to do that like we've done before. So we're going to convert our 25 milliliters into liters. That would be 0.025 times 0.1. Going to give us an initial moles of 0.0025 moles. And do the same thing with our sodium hydroxide, 0.021, which converts our milliliters into liters, and times in it by 0.1 gives us 0.0021 moles of this guy and 0 that guy. And again, so that calculation is, go here, 0.021 liters times the molarity, which is moles per liter, going to get us 0.0021 moles of sodium hydroxide. Again, same calculation was done with for acetic acid. Now I could actually kind of do a quick look at these two things and go, all right, this is definitely what I started with. This is what I'm adding. And I can see that the moles of what I'm adding is less than the moles of what I'm starting with, which means I am definitely before the equivalence point here because of that. Again, the moles of what I adding less than the moles of what I'm starting with. That also helps me understand that since I'm before the equivalence point, that means whatever moles I'm adding should be the change part, right? And the change here then should be 0.0021, 0.0021 plus 0.0021, going to get us now 0.0025 minus 0.0021. 0.0004 moles of this guy. Put the right number of zeros there. Nothing of this guy. 0.0021 moles of this guy. Any questions on the ice table so far? At this point, we want to convert these guys back into molarity so we don't mess up anywhere. We need the total volume. So our total volume at this point is the 25 milliliters we started with of the acid plus the 21 milliliters of our base that we added in. That gives us a grand total of 46 milliliters. And we're going to use that to convert these guys back into molarity. So again, converting that into liters and dividing by it will get us some molarity here. These guys, 0.0004 divided by 0.046 gets us something like 0.00896, I'll call it. I'll go a little bit more decimals. 0.0021 divided by 0.046. Going to give us 0.04565 molar. Any questions so far? Now, if you're not sure what is going on, which you really should kind of be sure what's going on even before we do this calculation. I'll talk about that here in 1 second. But we could use our ice table here to kind of figure it out. At this point, I got some acetic acid there. I got some sodium acetate there. Again, those two things are definitely related to each other. These two things are a buffer. Any questions on that? So what did I mean by you should actually have known that before we got here? At the point where we determined that we were before the equivalence point, we should know that that would put us before the equivalence point right here in this titration. And in this type of titration, before we even did the calculation, we should know that we should end up in a buffer situation. And this is why it's important to understand where you're at and what should be going on, because if you do, you obviously would know that you should hit a buffer at this point in your calculation. If you didn't hit a buffer at this point in your calculation, you clearly did something incorrect. So these are the ways you could kind of check yourself as you're doing these problems to make sure that you understand, what is going on. Any questions on that there? Well, that leaves us now the pH, which means, hey, we have two options. Since it is a buffer, the better option might be just to go right into our Henderson-Hasselbalch equation. You, again, could do another ice table if you wanted to. I'm not going to do that. I'm going to go into the Henderson-Hasselbalch. We need to get the pKa value, which is minus the log of Ka. That's going to be minus the log of 1.8 times 10 to the minus 5, which would be a 4.74 on the pKa. Putting that into our Henderson-Hasselbalch, 4.74 plus the log of the base, also important to recognize. Again, this is the base. We also know that because that guy is the acid because he has the Ka value. That means we're going to put this guy up on top. So 0.04565 divided by our acid there on the bottom, 0.008696, going to get us Looks like maybe a 5.46 in terms of our pH at this point. Question on that calculation there. You can see how we did, since this is the actual titration of this picture, I think. So we're at 21 and we ended up with like 5.46, which fits right in there. So by the way, these numbers are always specific for the example I wrote. They're not every titration, but this happens to be the titration that this curve was made from. And that's 5.46, which obviously puts us in the right spot there. So you can see that a couple of things are really important when we do titration problems, just to kind of wrap it up here. Knowing where you're at, knowing what type of titration it is, and it can also lead you, obviously, knowing before you begin, if you know where you're at, what type of problem that you should be doing. Again, all these different types of problems are all problems that we have done previously. The key in these situations is to make sure that you can identify what type of problem you're doing so that you can do the calculation correctly. Any questions on titration so far on the weak acid, strong base, or whatever we talked about today? Okay, so if there's no questions, obviously we will stop here.